Hello and welcome to the virus and threat protection lesson 14.4 on length of curves. I'm not sure why that thing decided to pop up. So we are going to take our formula from Calculus3, which was given by length of curve. L is equal to integral from a to b square root of 1 plus f prime squared of x dx. So that was the length of curve. Just in case if you are wondering, well, hold on, area, right? It should be area because it's integral. Well, if you consider that the square roughly cancels the square root and the integral roughly cancels the derivative, then you just have f of x floating around, and that's just one dimension, so length is a one-dimensional entity. So dimensionally, this equation makes sense. It's very easy to derive this equation because if you have some kind of a curve and now this is a Calc2 derivation, and you draw a delta x and delta y, and then you say, just approximate this with a straight line and call that lowercase l, you can immediately see that you can write the equation of L squared equals delta x squared plus delta y squared, from where L is equal to square root of delta x squared plus delta y. Yeah, it's a plus minus square root, but lengths are never negative, so we ignore the minus sign. And now, if you pull out delta x squared, you will have, if you factor out delta x squared from both terms, you would have delta x escape the square root as a single, and you will have 1 plus delta y over delta x, everything squared. And you already see the feature, right, of our formula, because delta y over delta x, when you send a number of these representative rectangles, delta x widths, to infinity, this delta x here becomes the dx for the integral. It turns into the formula. So it's a 3 steps derivation to come up for the calculus 2. This is Cartesian coordinates, rectangular, right, in 2D. So what I want now is to come up with the equivalent formulas for this for parametric equations first, because parametric equations are easily operating either 2D, 3D, 4D, whatever D space. We can deal with parametric equations very simply. So to convert this to parametric equations, so now we're working on parametric form. Parametric form. So now we're working on a parametric form. We start with our equation L equals integral a to b of a square root of 1 plus, and I'll write dy over dx. I'll use the Leibniz notation here, squared dx. So what I'm going to do, and this is the derivation that honors absolutely must know, I'm going to multiply everything by dt over dt. It's just, quick mathematical manipulation for us to work it out. So now the way the calculation goes, you quickly rewrite this as dx over dt, and then you have dt on its own on the side. So you just move this dt under dx. And now this dx dt will undergo square root, and when it goes under square root, it picks up a square. So the problem now becomes dx dt squared, because it went from outside, is stuffed inside, times 1 plus dy over dx squared, and you have dt on the outside. So now when you distribute this, you are done. You see that you get dx dt squared times 1 is dx over dt squared. And then dx squared will cancel, dt will remain, so plus dy dt squared and then dt. So there you have it. So now you will say, let r, right? Let r of t be given by x of t and y of t. Then length of curve, where t is between a and b, length of curve will be given by just the derivative, so it's just x prime squared plus y prime squared dt. So this is your formula, and it's as simple as just adding these components. Now this is your formula for R2, and if you want R3, you just stuff z under the radical there, so z prime squared. So we'll have the length of curve, it goes a to b, square root of x prime squared plus y prime squared plus z prime squared dt. And let's go purple on this one. So that will be your R3. Now some of you are quick to notice that you have the squares of the x and y and all of these primes, and that would be the speed, right? Because it's the velocity. So you can also recast this as a multi-dimensional vector. This is the way I like to memorize stuff, because you remember one equation that works in any dimension, and that's going to be the integral of velocity vector dt, because now this is any dimension. So you want to calculate the length of the path in a 6-dimensional vector, fine. You're just going to have x, y, z, and then another 3 variables there. The book is not using v. The book is using magnitude of r prime. So book is using magnitude of r prime. We know that velocity is r prime. So we had that in the previous 2 lessons. So here are your parametric form, and the great thing about parametric form is that they work in any dimensional space. So whether it's R2, R3, or R7, whatever, it works great. And now we are going to take a look at the example for this. So let's say that you would like to calculate the length of the curve for 1/8 of the circle. So what is L for 1/8 of the unit circle? Well, first off, what is the 1/8? Well, that's exactly 1 pizza slice in a large pie, right? The pizza is cut 4 ways, and then you cut each one right on the side. So if you take a look at the unit circle, radius is obviously 1. You cut also this way, so this much over here is 1/8 of the full circle. And they're asking what is the length. Now clearly you can compute this without calculus. What's the circumference of a circle? Very good. And since radius is 1, it's just going to be 2 pi. And because you want 1/8 of it, the length we are looking is 2 pi over 8. So pi over 4. So the answer we are looking for is pi over 4. Now, obviously, why simple if we can complicate things? So let's do the integral, right? I mean, maybe you are tutoring a kid and they come up with the famous question, why? time to do the integral. So you would say to this kid, the unit circle, the parametric equations for unit circle are given by r equals, since the radius is 1, you can just write cosine t sine t. So those are the parametric equations. And your angle will be 0 to t to pi over 4, because you only want an 1/8 of a circle, right? All the way north is going to be pi over 2, and then flat is pi. So since you want only one part is 1/8. Now the length of curve is going to be given as 0 to pi over 4, and then you have a square root, and here is the derivative of the first one squared, so that's going to be your sine squared t plus cosine squared t dt, integral 0 to pi over 4 of, and sine squared plus cosine squared is 1. So you are just integrating dt, which is t calculated from 0 to pi over 4, is equal to pi over 4, and it's immediately clear why the length is what it is. It's a good thing to bring up during, let's say, Thanksgiving dinner, or at the next party you see pizza, right? And calculate the length of the. And now we are left with polar form. Now, for polar form, we need to remember few things. One of those would be that x is equal to r cosine theta, and y is equal to r sine theta as the conversion. So we need to have that on the side, because what I'm going to do here is I'm going to write my parametric form. So the length of curve is given as integral a to b of square root of, and I'm going to write this as dx dt squared plus dy dt squared. Yeah, I understand that you like your x primes and y primes, but it is much better for calculations if you are using Leibniz notation. Now we are going to do the same trick as earlier, because we are switching now from parameter t into parameter theta. I'm just going to hit this with d theta over d theta. The next step is the same as before. Now, since we are shifting from time t into the theta domain, we're going to switch these limits to be alpha and beta, because now the input is the angle. Input is whatever angles you get in terms of radians. So, I don't know, pi over 4 and 3 pi over 4 and so on. All right, so the next step is to just get this, you copy this, and you get your dt over d theta, and then times d theta. So now dt d theta is ready to go inside. Dt will become dt squared. It will kill all the denominators, and then d theta will take over as a d theta squared. So we are getting alpha, beta as limits, and then the square root of dx d theta plus squared plus dy d theta squared d theta. And this is the reason why we needed those formulas. We needed to remember those formulas. Actually, maybe I should just move those formulas down next to the place where we actually going to use them. You are not allowed to leave the formula in terms of x's and y's, where all of your input variables are only allowed to be theta and r. So you have to reconfigure your equations here. Well, the first thing is that this r, the way we defined functions in calculus 2 for polar coordinates, we said that r is equal to f of theta. So that's right. That was the basic premise there. So we can say x is f of theta cosine theta, and y is f of theta sine theta. So these are the formulas that we are going to use in our calculus, in our calculation. So as I replace the x only over here, as I replace x with f prime cosine, you see that you have to do some product rule to work it out. So d theta of f of theta cosine theta is given as copy the first times derivative of the second, which gives you a negative sine theta, plus copy the second, which is cosine theta, times the derivative of first, so that's f prime. And now, because the first term has a negative, just write f prime of theta cosine theta minus f of theta sine theta. So all I did is I took the derivative of x and I came up with the first rule. Now I can just put x prime over here. How about that? So now y prime would be the derivative in respect to theta, and now you have f of theta sine theta. It's the product rule again. I'm just going to skip over that stuff and just have f prime of theta sine theta plus f of theta cosine theta, because I already know it. Now you are going to feed these here and square them and subtract the like terms and all of that stuff. So plug in for dx dt squared and dy, not dt, d theta squared, and expand. So I'm just gonna skip that stuff so we are not staying here for dinner as well. And you will get to the length of the curve is equal to alpha to beta of the square root of f of theta squared plus f prime of theta squared d theta. So that's our formula to calculate length in polar coordinates, which is for some problems obviously much easier to use than what we are used to of seeing there. So now what I can do here is do the same problem with the circle that we know the answer for. But the cool thing now is that unit circle is now given as r equals 1, which is actually f of theta equals 1. Well, that's going to be a joke, right? And your thetas, because we want only 1/8, are stuck between 0 and pi over 4, right? We only want 1/8 of a circle. So now if you're calculating the same problem as earlier, you still have 0 to pi over 4, and now you have a square root of 1 squared plus 0 squared d theta. Well, that just make a joke of a problem, right? Because we are dealing with a circle, and a circle is one of the very basic things we can write in polar. So integral 0 to pi over 4 of d theta is equal to right, theta, and then pi over 4 minus 0 is pi over 4. So this made the problem even easier. Now, some of you might be going, why 3 formulas for the same concept? Well, each one of these formulas is going to hold for a particular type of problem. You did not see me do this problem in rectangular coordinates, right, with a circle, because you will be a living nightmare to do it in that one. So all of these formulas will be easy to use, great to use when the formulas, I gotta restart this sentence. We gotta reboot. Each one of these formulas is going to be used in its own realm. Let's put it that way. So, if you have a circle, you have a flower, cardioid, all of that good stuff, obviously you should be using polar coordinates. Now, all of those are also 2D. If you run into a 3D problem, well, the only way you can deal with the 3D is a three-dimensional parametric equation. So, these formulas complement each other in a sense that each one of these formulas work wherever they're effective. Now, do you really want to work this problem out in terms of the function as y equal f of x? Well, hell no, right? Because the circle is going to be given by the square root y equals plus minus square root of 1 minus x squared. Great. Now you have to take the derivative of that and then stuff that inside the 1 plus derivative squared. It's just going to make crazy, and then you will end up using something that you haven't learned yet, which is, no, wait, call this Calc3, you learned it. Then you have to use the trig sub to solve the integral. It's just so much pain for, look at this, right? So the idea is that the problems that are supposed to be done in rectangular coordinates, you are free to use the Calc2 formula and maybe even parametric one. 3D problems, 100% done with parametric, right? Some of the 2D ones maybe you want to do in parametric form. And then anything that deals with circles and flowers and cardioids and annulus and whatever, those flowers with petals and stuff, that's all going to be polar. So 3 formulas, they all operate in their own realm, and one of these 3 obviously you learned in Calc2, and that's the one we use to develop all the others. So you guys have the derivation. In terms of calculations, some problems will tell you which formula to use, others will not. You will have to make a choice. On the exam, obviously, you'll have one of these, not all 3, and you guys might have to just do the calculation, like the derivation for one of them. So that's the thing. Questions, concerns? No? Shall we do another example? We do have time. Yeah? Okay. Sounds good. How about you pick something from this list of homework assignments, and we're just going to work out a problem.
10.
Which one? Number 10. Number 10 says, so we have a linear, we can use the distance formula on this one. We don't need a length of curve. You have the endpoint at 0, which is 0, 0, 0. You have the endpoint at 1, which is 2, 9, 1. And you just run the distance formula from 0, 0, 0 to 2, 9, 1. And you're done. So 10 is a linear problem. We don't even need these techniques. However, if you are to solve this, right, let's say you like pain, and you do want to use the length of curve integral on that one, which one would you pick? Length of curve for Calc2, parametric, or polar? Which one you must pick? Parametric, because it's a 3D problem, right? It has 3 equations. Remember, polar coordinates is a strictly 2D. You only have theta and r. So it's strictly 2D. Calculus 2 problem length of curve, strictly 2D. You learned it in Calc 2. The only one that can deal with the 3D problems is going to be parametric. So you see a vector of 3, parametric. If you see a vector of 2, then all 3 methods apply. You figure out which one is the fastest, or which ones are possible. right? You get a flower, well, the only one you can use is a polar, right? If you get a flower curve. All right, so what else? We tossed 10 out of the...
About 18.
18, okay, great. So 18 has a little bit of mess there. And what I see for the problem 18, well, definitely I do not want to play with the calculus 2 length of curve here because I don't have a nice environment where I can easily express y equals as the terms of x when I put these things together. Try it, you'll see. Now, this is not polar because it's not circles and so on, so we are actually stuck with the 2D parametric on problem 18. So it's a process of elimination to figure out which of the three formulas is easiest to use or just possible to use. So problem 18 says that r of t is given as t squared over 2 and 2t plus 1 to the 3/2 divided by 3, and the t is between 0 and 2. All right, let's take a look at this together. So I know I need the r prime vector, so that's going to be t, and I have to take derivative of this, so it's going to be 1/3 times 3/2 times 2t plus 1 raised to the 1/2 times the derivative of 2, which is the derivative chain rule, right? Derivative of the inside. So now 3 kills 3, 2 kills 2. Well, that's nice. So we have our r prime to be t and square root of 2t plus 1. Nice. The length of curve using parametric for 2D, 0 to 2. Now, the first one squared, that's t squared, plus the second one squared, the square root dies. So I just have 2t plus 1 dt. Perfect. Well, let me just put the steps. So this is like this, and then I square it, so I'll kill it in the next term. So 0 to 2, t squared plus 2t plus 1 dt. There we go. So we plugged it into a formula. And now we need to integrate this. What's the only thing that I can do? I don't have a t in front. I need 2t plus 1 in front in order for 2t plus 2. A t plus 1 will be sufficient to do u sub. So u sub is out. What else? This is why we need to cover 8.1 before you hit the exam, because 8.1 reviews this method. Anyone? Yes. We are going to factor this, which will actually give us the perfect square, and then that will kill the square root. So we go 0 to 2, and then this condenses into t plus 1 squared dt. So that's the algebraic manipulation. So you have basic integrals that you have to massage with algebra, and then you have the u sub. So those are the only options that you have until we're done with chapter 8. So now the square and the square root annihilate each other. There we go. And you are left with the integral 0 to 2 of just t plus 1 in parentheses dt. That's going to be t squared over 2 plus t from 0 to 2. 4 divided by 2 is 2, plus 2 minus 0 is 4. So the answer is 4 for the length of curve. 4 units, whatever. meters, centimeters, inches, whatever the problem was measured in. So that's problem 18 from the homework. I encourage you definitely to check out Helix, because Helix calculations work very, very well. And then I think there is a problem that looks terrible, but it's easy, and then there is a problem that looks easy, but it's terrible. That's going to be an interesting thing for you to discover. Something like problem 40, for the arc length, and so on. See you tomorrow. Bye.